Hello, my name is Santiago Balseiro. I'm going to present the landscape of autobidding auctions, value versus utility maximization. This is shown work with Yuan Deng, Jieming Mao, Vahab Mirrokni, and Song Su from Google Research. So the motivation from this work comes from the fact that internet advertisers are increasingly adopting automated bidders to buy advertising opportunities in order to navigate the increasing complexity of advertising markets. Now, automated bidders simplify the procurement process by allowing advertisers to specify high-level goals and then bidding on their behalf in the advertising auctions. Now, the issue is that current auctions that are used in practice do not explicitly account for automated bidders and their advertisers' goal. So then, as automated bidders are increasingly adopted, it's important for us to understand how can we design better auctions from the seller's perspective that maximize revenue. In order to understand the question, we need to rethink where advertisers' goal and their prior information in the auto-bidding world. Now, the classical paradigm in economic theory and mechanism design is that of utility maximization. That says that advertisers should maximize their quasi-linear utility, which is given by the difference between the value and the payment. Now, in this market, it is the case that most advertisers actually what they seek to maximize is their value. That could be like clicks or conversions, subject to a return on spend constraint. What do we mean? Well, they're solving this maximization problem. They're maximizing their value without any payment in the objective, but then payments are indirectly captured in this return on spend that says that the ratio of value to payment should be greater than the target that they specify. And this value maximization model is a common strategy that is being adopted by many advertisers in the auto bidding world. Now, another common assumption in the literature is in terms of prior information is that values of the advertisers are private and their targets are public. Now, for automated bidders, these assumptions might not hold. Why? Are values really private? If you think of values, these are driven by clicks or conversions. And it is the case that the platform have like very sophisticated machine learning models that they use to estimate these clicks and values. And in many cases, they may end up having like better prediction than advertisers, and advertisers would rely on these predictions. So advertisers have like less incentive to strategize their values. So from this perspective, we can think of them as being public. In terms of the targets, are targets really public? If you think about targets, they depend on how advertisers internally evaluate their advertising campaign relative to other marketing channels. And this depends a lot on their return on accounting. So it's also reasonable to assume that the target itself is private. So what's our goal and contribution? Our goal in this paper is to understand the impact of advertisers' prior information and their different objectives on the seller revenue. In order to achieve this goal, we introduce a sequential screening model with two stages. In the first stage, advertisers are going to report their targets. In the second stage, advertisers are going to report their values, subject to the return on spend constraint that is going to be satisfied in expectation. We're going to provide a novel characterization of assembly compatibility for this sequential screening model, and we're going to leverage this characterization to characterize optimal mechanisms under different information structures and different advertiser objectives. We're going to try to understand whether the first best revenue, that is the optimal revenue that you can achieve when all prior information is public, is achievable. And in doing so, what we hope is to take a first step towards mapping the landscape of auto bidding options. So let me give you a preview of our results. We first start with value maximizers. In the case of value maximizer, we explore different information structures. First, we look at the case when targets are private and values are public. In this case, we show that first best revenue is achievable, and this is actually achievable by a very simple mechanism that is a first price auction over target adjusted values. What do we mean? Is that for each advertiser, we compute the value over the target. We rank them in this order. The one with the highest ratio wins, and is going to pay their bid. Now, then we switch to the case of values being private and target being public. In this case, we show that also the first best revenue is achievable, but this is achieved by a different mechanism that is a payment scale second price auction. And then we move to the case of both targets and values being private. In that case, we show that first best revenue is not achievable in general. And characterizing the optimal mechanism is an interesting question that we leave open. Then we switch to the case of utility maximizers with a return on spend constraint. In this case, we look at the same information structures. First, when targets are private, we show that first best in general is not achievable, and we characterize an optimal mechanism for the case of single buyer. And this is what we call the iron utility mechanism, that is trying to iron out the utility that the advertisers get. And we have like some new ideas in here. In the case of values being private, also we show that first best is not achievable. And here we show that an auction that essentially is a weighted combination of the traditional milestone auction with the target adjust values actually is optimal. And this may require some subsidies to satisfy the ROS constraint. And in the case of both targets and values being private, then this is another mechanism that we don't know how to characterize, and we leave it an interesting open question. So in terms of related work, again, there is some work in terms of auction design in the automated world, mostly around like price of anarchy results, try to understand what fraction of the optimal welfare you can get under standard auctions, that, for example, second price auction. There's also work on mechanism design for constrained buyers. Most of this literature focus on the case of budget constraint. The only exception is a recent paper by Goresai et al. That looks at ROS constraint, and some of our mechanisms actually coincide with the ones that they derive by the IC constraints are different. And also work on budget pacing for advertising platforms. Now, in terms of the outline for this talk, I'm going to start with the model and the mechanism design problem. Then I'm going to talk about value maximization and the different information structures. Unfortunately, I don't have time to talk about utility maximization. If you want to learn more about that, I encourage you to look at the paper. Some of the most technical challenging aspects of the paper are in the case of utility maximization. So I think it's interesting too. So I encourage you to look at that. And then I conclude with some final remarks. Now, our model, we're going to assume that we have n bidders and one slot that is being auctioned. Bidders have value Vi that are drawn independently from some distribution Fi. And bidder I has a target tau that is drawn from another distribution. We're going to assume for this talk that bidders are value maximizers with a return on spend constraint, or ROS for short. That means that bidders are maximizing the respective value subject to the constraint that the ratio of values to payment should be greater than the target. Here, instead of writing this as a fractional constraint, we linearize it and write it as this equivalent mathematical form that is more amenable to analysis. In terms of the sellers, we want to focus on direct mechanism by the relation principle. What is a sequential screening mechanism? X and P. The first component, X, is the allocation that is going to determine, based on the target and the value reports, who gets allocated the item. So this should satisfy that should be at most one, and all of them non-negative. And then a payment based on the target and the values that are reported. Now we're going to model our problem as a two-stage game in which bidders first report their target, and then they're going to report their values to satisfy the return on spend constraint. Now, one important modeling assumption is that we're going to satisfy the return on spend constraint in expectation over all bidders' values, and we're going to collapse what in practice is some repeated auctions into a single auction. This is going to be a single period model with an expectation constraint that is meant to capture the complex dynamics that actually occur in the market, and this is something that has been adopted by many other papers in the literature. Now, in terms of incentive compatibility, we're going to say that a mechanism is incentive compatible if every bidder, when everybody else is reporting truthfully, it should be first better off reporting her true value when she reports her true target ratio in the first stage, and also in the first stage should be better off reporting her true target. Okay. Now, mathematically, how do we write this down? We need to define this object that we call UI tau hat of tau that essentially captures the optimal payoff that a buyer can get from jointly deviating in terms of their target to a target tau hat, and also in terms of their values. Now, if this bidder I deviates in terms of their target and also deviates on their values, now the deviation of their values is more complex because we allow for randomized bidding strategies that they are meant to, again, maximize the expected value they get from misreporting, and they satisfy the ROS constraint in expectation. Okay, so the value that you get from misreporting minus the original target tau times the payment should be greater or equal to 0, and taking expectation over all values and also the randomization of the strategy. Now, with this notation, we have that reporting of HER2 target. What it means that you should always be better off reporting tau instead of tau hat. And also, in the first condition, what we mean is that if you report your true target, then you should always be reporting your value. Now, one point that I want to emphasize is that incentive compatibility doesn't preclude deviation of equilibrium. Now, if you misreport your target, then reporting your true value may not be optimal. You may be better off reporting a different value, and this is going to be an important consideration for our results. Now, in terms of the seller's problem, seller is maximizing revenue that is given by the sum of the payment subject to the incentive constraints. We're going to benchmark our mechanisms against first best, that is the optimal revenue when all information is public. And it has the same objective, but now we relax incentive compatibility and we only need to satisfy the return on spend constraints. Now, a first result is that the first best mechanism is actually given by a first price auction over target adjusted value. So what's the meaning here? If you have no prior information, what you're going to try to do is you're going to set payments as high as possible to make the ROS constraint bind. And this is achieved by allocating to the bidder with a higher value to target. That's what we call the target adjust value, the ratio of value to target. And then you charge the value over the target of the winner. Okay? And this is the first best mechanism. It's going to play an important role in our analysis. So let's move to the first setting, value maximization with private targets and public values. So we first provide a characterization of incentive compatibility, and we show a mechanism is incentive compatible in terms of the target if it satisfies the following two requirements. The first requirement is very intuitive. That says the payoff that you get from reporting your true target should be decreasing. Why? Well, it's always the case that a buyer can impersonate one with a higher target because that would only give you higher return on spend. So in order to prevent that deviation, the payoff should be decreasing. The second condition is a little bit more subtle, and it says if you want to report a lower payoff, a lower target, and this target gives you more utility, well, it should be the case that that's not feasible for you, in the sense that the expected return on spend that you get from that deviation actually should be below your target. Okay, and these two conditions are necessary and sufficient with public values. And in this case, we can show that the first mechanism, the one that we just mentioned a few minutes ago, actually satisfies incentive compatibility. Why? Well, by construction, the mechanism always satisfies the return on spend constraint. And if you write the utility, you're going to see the utility is increasing on your target. Why? Well, remember that buyers are ranked in terms of the value over the target. So if you report a higher target, then V over T is going to decrease. And that would mean that the chance of winning is going to decrease and your utility is going to decrease. So that's kind of why this mechanism is IC. Now, let me move to the case of public targets and private values. In the case of private values, we also provide a characterization that is necessary and sufficient for incentive compatibility. And it goes as follows. For each bidder, there should exist a multiplier gamma I. And this should satisfy two conditions. The first condition says that bidding your true value should maximize the expression in braces. And the expression in braces, we have first the target adjusted value, Vi over tau I, times the interim allocation. That's the probability that you get the item, minus the interim payment, times this multiplier that is gamma I over 1 plus gamma I, that is scaling off the payments. And the second condition is very intuitive. What it's saying is you should satisfy the ROS constraint. Also, the multiplier should be greater or equal to 0. And this multiplier, you can interpret it as a Lagrange multiplier of the ROS constraint. So what this condition is saying that it should satisfy a complementarity condition, that one of these should always be holding with equality. Now, if you look at the first condition, what it tells you is that you can actually reduce our problem of value maximization with ROS constraint to that of a quasi-linear utility maximizer in which the values are V over tau, and now payments are evaluated in terms of this new factor that is like the scaling that is gamma over 1 plus gamma, plus the additional constraint. Now, using this characterization that we actually prove using duality theory, we can actually characterize optimal mechanisms, and we can show that the optimal mechanism is a payment scale second price auction. How does it work? You allocate according to the first best mechanism as before, but now the payments are that of a second price auction in the sense that the highest bidder is going to win and it's going to pay the second highest target adjust values. But now you are scaling this by the payment multiplier given that 1 plus gamma over gamma, where gamma are chosen so that the return of spend binds. And moreover, we can show that this mechanism achieves first best revenue. How do you prove that this mechanism is IC? Well, if you plug in this mechanism into the lemma, you're going to see that this is going to reduce to a second price auction with values V over tau for a quasi-utility maximizer. And using standard results, you can prove that this actually is IC. And a similar analysis holds for first best revenue because you are allocating efficiently, and also the return on spend constraint is always binding. Now, for the case of private targets and values, the characterization that we gave for values is necessary and sufficient, but the characterization that we gave for target is necessary but not sufficient. Here we can give another characterization that is linking the first and second stage IC, that is saying that the derivative of your payoff with respect to your target should be linked with your multiplier gamma in the following equation. And then using this formula, we can actually prove this result that says that when both values and target ratios are private, there exists an instance in which first best revenue is not achievable. How do we prove the result? Well, to achieve first best, you need to allocate according to the first best or the efficient allocation. This is going to pin down your utility. In a case of value maximization, this is going to be value times allocation. Now, using the condition that I gave you there in asterisk, that's going to pin down, if you're given your utility, it's going to pin down the multiplier gamma. And now, if you have the multiplier gamma and the allocation, you can use the characterization of IC that we have together with Meyerson formula to fully characterize the payments. Now, you already have the allocation, we have the payment, so the mechanism is fully specified. And now, once we fix the mechanism, we can show that bidders have a two-state deviation that is beneficial. So they can misreport their targets and their values, and this could be profitable, and that implies that first best is not achievable. So to sum up, here we initiate the study of mechanism design for auto bidders with return on spend constraint. We explore different objectives and different information structure. We show that first best is only achievable for value maximizer with private values or target, but not both. And in doing so, again, we are challenging classical modeling assumptions, and we also hope to bring forward some new challenges that arise in the auto bidding world. Again, there are lots of future directions and open questions that we feel are interesting. For example, in the case of utility maximizer buyers with private targets, we only can characterize mechanisms for a single buyer. What happens if you have multiple buyers? Also, in the case of private targets and values, we have like partial characterizations. Can we characterize optimal mechanism? And also, it will be interesting to incorporate additional operational constraints, such as budgets, to our model. Thank you.